Introduction.
Hey, Pinky, let's go back. I have to study. No, wait. Come, I will show you something. What? Say something loudly. Pinky! Wow, what is this? This is called the echo. Echo? Interesting. Yes, echo of the sound. Do you want to know more about this? Yes, please tell me. Come, today I will tell you everything about sound.
Objectives.
At the end of this lesson, you will be able to understand the production of sound, understand the propagation of sound, write the characteristics of sound waves, understand the reflection of sound, define echo and reverberation, describe sonar, and explain the structure of human ear. Production of sound. Students, we know that sound is a sensation or a feeling that we hear. Sound is produced with a vibrating object. The motion of materials or objects causes vibrations. Vibration means a kind of rapid to and fro motion of an object. Let us look at some examples of how certain sounds are produced. Human voice. The sound of the human voice is produced due to vibrations in the vocal cords. Animal sound. When a bird flaps its wings, a sound is produced. Bees buzz as they fly because of the rapid movement of their wings. Their wings make the air vibrate, producing a buzzing sound. Musical sounds. Musical instruments produce many different sounds in various ways. Some instruments need to be struck by an object in order to produce a sound, while some instruments, such as a harp or a violin, produce sounds when one or more of their strings are plucked, causing them to vibrate. Propagation of sound. For sound to be generated and heard, it must have three things. They are a source, a medium through which to pass, and a receiver. Let us assume the source is the speaker's voice, the medium through which it is transmitted is air, and the receiver is the listener's ear. When a sound is generated by the speaker's speech, or when an object vibrates, it sets the particle of the medium around it vibrating. The particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. It then exerts a force on the adjacent particle, which gets displaced from its position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches your ear. During propagation of sound in a medium, the particles of the medium do not move forward themselves, but the disturbance is carried forward. So, sound waves are characterized by the motion of particles in the medium and are called mechanical waves. Can you tell the most common medium of sound? Air is the most common medium through which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression. And when the vibrating object moves backwards, it creates a region of low pressure called rarefaction. The compressions are region of high air pressure while the rarefactions are regions of low air pressure. Look at this image. It shows a sound wave created by a tuning fork and propagated through the air in an open tube. These are the regions of compression and these are the regions of rarefaction. Sound needs a medium to travel. As sound is created by the vibration of particles, it requires a medium such as air, liquid, or a solid. But how can we prove that it needs medium to travel? Let's see. Look at this figure. Here, an electric bell is suspended inside an airtight glass bell jar connected to a vacuum pump. As the electric bell circuit is completed, the sound is heard. Now, if we slowly remove the air from the bell jar by using a vacuum pump, the intensity of sound goes on decreasing and finally no sound is heard when all the air is drawn out. We would be seeing the hammer striking the gong repeatedly. This clearly proves that sound requires a medium for its propagation. Sound waves are longitudinal waves. A wave in which the particles of the medium vibrate back and forth in the same direction in which the wave is moving is called a longitudinal wave. Longitudinal wave can be produced in all the three mediums: solids, liquids, and gases. Sound waves are longitudinal because the direction of vibration of the particles is parallel to the direction of wave. When a sound wave passes through air, the particles of air vibrate back and forth parallel to the direction of sound wave. Thus, when a sound wave travels in the horizontal direction, then the particles of the medium also vibrate back and forth in the horizontal direction but parallel to the direction of sound. For example, the waves produced in air when a violin wire is plugged are longitudinal waves. There is also another type of wave called a transverse wave. A transverse wave is the one in which the individual particles of the medium move about their mean positions in a direction perpendicular to the direction of wave propagation. Characteristics of a sound wave. A sound wave can be described by three basic qualities, that is, its frequency, amplitude, and speed. The number of times the wavelength occurs in 1 second is called frequency. It is measured in kilohertz or cycles per second. The faster the sound source vibrates, the higher the frequency. Higher frequencies are interpreted as a higher pitch. For example, when you sing in a high-pitched voice, you are forcing your vocal cords to vibrate quickly. Thus, a high-pitched sound corresponds to more number of compressions and rarefactions passing a fixed point per unit time. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of different pitch. It is usually represented by a Greek letter nu. Its SI unit is Hertz. We know that compressions are the regions where particles are crowded together and represented by the upper portion of the curve. The peak represents the region of maximum compression. Thus, compressions are regions where density as well as pressure is high. Rarefactions are the regions of low pressure where particles are spread apart and are represented by the valley, that is, the lower portion of the curve. A peak is called the crest and a valley is called the trough of a wave. The distance between two consecutive compressions or two consecutive rarefactions is called the wavelength. The wavelength is usually represented by a Greek letter lambda. Its SI unit is meter, m. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. It is represented by the symbol T. Its SI unit is second. Frequency and time period are related as nu is equal to 1 upon T. The strength or power of a wave signal is called its amplitude, or the height of the wave when viewed as a graph is the amplitude. The loudness or softness of a sound is determined basically by its amplitude. The amplitude of the sound wave depends upon the force with which an object is made to vibrate. Speed. The speed of sound is defined as the distance with which a point on a wave, such as a compression or a rarefaction, travels per unit time. We know that speed, u is equal to distance upon time, which is equal to lambda upon t. Here, lambda is the wavelength of the sound wave. It is the distance travelled by the sound wave in one time period of the wave. Thus, u is equal to lambda into nu. That is, speed is equal to wavelength into frequency. Speed of sound in different media. The speed of sound depends on the material through which it's passing. It is greater in solids than in liquids or gases because the molecules in a solid are closer than in a liquid or gas. In this table, you can find the speed of sound in different media at 25 degrees Celsius. Reflection of sound. Like light, sound also gets reflected at the surface of a solid or liquid. The reflection of sound follows the same laws as for reflection of light. Angle of incidence is equal to the angle of reflection. The incident wave, reflected wave and the normal lie in the same plane. Sound waves can be reflected by large, hard, smooth, vertical and faraway surfaces. Example, walls, buildings and cliffs. Echoes are produced by the reflection of sounds from such surfaces. The sensation of sound persists in our brain for about 0.1 second. To hear a distinct echo, the time interval between the original sound and the reflected one must be at least 0.1 second. If we take the speed of sound to be 344 meters per second at a given temperature, say 22 degrees Celsius in air, the sound must go back to the obstacle and reach back the ear of the listener on reflection after 0.1 second. Hence, the total distance covered by the sound from the point of generation to the reflecting surface and back should be at least 344 meters per second into 0.1 second is equal to 34.4 meters. Thus, for hearing distant echoes, the minimum distance of the obstacle from the source of sound must be half of this distance, that is 17.2 meters. This distance will change with the temperature of air. Echoes may be heard more than once due to successive or multiple reflections. Reverberation. The repeated reflection that results in this persistence of sound is called reverberation. A reverberation is perceived when the reflected sound wave reaches your ear in less than 0.1 second after the original sound wave. For example, a sound created in a big hall will persist by repeated reflection from the walls until it is reduced to a value where it is no longer audible. Let's now solve a problem. A person shouts near a cliff and hears the echo after 5 seconds. What is the distance of the cliff from the person? If the speed of the sound, v, is taken as 300 meters second raised to the power minus 1. Given that the speed of sound v is 300 meter second raised to the power minus 1. Time taken for hearing the echo, t, is 5 seconds. Distance travelled by the sound is equal to v into t, which is equal to 300 meter second raised to the power minus 1 into 5 seconds is equal to 1500 meters. In 5 seconds, sound has to travel twice the distance between the cliff and the person. Hence, the distance between the cliff and the person is 1500 meters by 2, that is 750 meters. Range of hearing. The average person has a normal hearing range that falls between 20 Hz on the low side and approximately 20,000 Hz on the high side. Children under the age of 5 and some animals such as dogs can hear up to 25 kHz. The hearing range of humans gets worse with age. People lose the ability to hear sounds of high frequency as they grow older. Sounds of frequencies below 20 Hz are called infrasonic sound or infrasound. Some animals like whales and elephants produce sounds in the infrasound range. Frequencies higher than 20 kHz are called ultrasonic sound or ultrasound. Dogs can hear some ultrasound, thus a dog trainer can use an ultrasound whistle to call his dog. Ultrasound is even more important for bats because they rely on ultrasound to see the world. Applications of ultrasound. We use ultrasounds in industries and for medical purposes. Ultrasounds are able to travel along well-defined paths, even in the presence of obstacles. The doctors use a high-frequency ultrasound handheld transducer to scan the mother's abdomen. It is generally used to clean parts located in hard-to-reach places, for example, spiral tube, odd-shaped parts, electronic components, etc. Ultrasounds can be used to detect cracks and flaws in metal blocks. Ultrasonic waves are allowed to pass through the metal block and detectors are used to detect the transmitted waves. If there is even a small defect, the ultrasound gets reflected back, indicating the presence of the flaw or defect. Ultrasound is used for echocardiography. In this, the ultrasonic waves are made to reflect from various parts of the heart and form the image of the heart. Ultrasound is also used to break small stones formed in the kidneys into fine grains. These grains later get flushed out with urine. Sonar. Sonar is the device that uses ultrasonic waves to measure the distance, direction, and speed of underwater objects. The word sonar stands for sound navigation and ranging. Sonar consists of a transmitter and a detector and is installed in a boat or a ship. The transmitter produces and transmits ultrasonic waves. These waves travel through water and after striking the object on the seabed get reflected back and are sensed by the detector. The detector converts the ultrasonic waves into electrical signals which are appropriately interpreted. The distance of the object that reflected the sound wave can be calculated by using echo ranging method. Let the time interval between transmission and reception of ultrasound signal be t and the speed of sound through seawater be v. The total distance 2d travelled by the ultrasound is then 2D is equal to V into T. This is the echo ranging method. Structure of the human ear. The ear consists of three basic parts: the outer ear, the middle ear, and the inner ear. Each part of the ear has a specific role in the task of detecting and interpreting sound. The outer ear is called pinna. It collects the sound from the surroundings. The collected sound passes through the auditory canal. At the end of the auditory canal, there is a thin membrane called the eardrum or tympanic membrane. The eardrum moves inward and outward as the compression or rarefaction reaches it. In this way, the eardrum vibrates. These vibrations are amplified by the three bones, namely the hammer, anvil, and stirrup in the middle ear. The middle ear transmits these vibrations to the inner ear. Inside the inner ear, the vibrations or the pressure variations are converted into electrical signals by the cochlea. These electrical signals are sent to the brain via the auditory nerve, and the brain interprets them as sound. Did you know? Heinrich Rudolf Hertz was born on 22nd February 1857 in Hamburg, Germany, and educated at the University of Berlin. He confirmed J.C. Maxwell's electromagnetic theory by his experiments. He laid the foundation for future development of radio, telephone, telegraph, and even television. He also discovered the photoelectric effect, which was later explained by Albert Einstein. The SI unit of frequency was named as Hertz in his honor. Hearing aid. People with hearing loss may need a hearing aid. A hearing aid is an electronic, battery-operated device. The hearing aid receives sound through a microphone. The microphone converts the sound waves to electrical signals. These electrical signals are amplified by an amplifier. The amplified electrical signals are given to a speaker of the hearing aid. The speaker converts the amplified electrical signal to sound and sends to the ear for hearing. Summary. Let us summarize what we have learned. Sound is produced due to vibration of different objects. Sound travels as a longitudinal wave through a material medium. Sound travels as successive compressions and rarefactions in the medium. Sound cannot travel in vacuum. The distance between two consecutive compressions or two consecutive rarefactions is called wavelength, lambda. The time taken by the wave for one complete oscillation of the density or pressure of the medium is called the time period, T. The number of complete oscillations per unit time is called the frequency, nu is equal to 1 upon T. The speed u, frequency nu, and wavelength lambda of sound are related by the equation u is equal to lambda into nu. The speed of sound depends primarily on the nature and the temperature of the transmitting medium. The law of reflection of sound states that the directions in which the sound is incident and reflected makes equal angles with the normal to the reflecting surface, and the three lie in the same plane. For hearing a distinct sound, the time interval between the original sound and the reflected one must be at least 0.1 second. The persistence of sound in an auditorium is the result of repeated reflections of sound and is called reverberation. The audible range of hearing for average human beings is in the frequency range of 20 Hz to 20 kHz. Sound waves with frequencies below the audible range are called infrasonic, and those above the audible range are termed ultrasonic. Ultrasound has many medical and industrial applications. The sonar technique is used to determine the depth of the sea and to locate underwater hills, valleys, submarines, icebergs, sunken ships, etc.